Miami. South Beach.
Oh, yeah. All right, let's go, folks. Let's do this. This is Mr. Los. This is HL Chemistry Flipped Classroom, and today we're going to talk about Hess's Law. What Hess's Law says is that enthalpy, or the energy you're going to get from reactions, is a state function, and it doesn't matter the pathway that you take. So, for instance, this is an example down here. Okay, this reaction isn't balanced, but this is the combustion reaction for glucose, but it's also the reaction that your body uses to get energy from glucose. Cellular respiration, the chemical reaction is exactly the same. So whether we're doing it in a series of steps, like happens in our body, or whether you're just burning glucose in air, theoretically the energy that you would get is the exact same in either way. So Hess's Law says the path that you take doesn't matter. Let me give you another example, or just another way to think about what a state function is. And I don't know that you need to write this down, but altitude change between 2 points on the globe is also a state function. So let's say you're just comparing the distance between the altitude change between 2 points, like for instance, lovely Denver, Colorado, and somewhere else. So I don't know, maybe good old Miami, Florida. Lovely place. I spent my honeymoon there. But suppose I'm traveling between Denver, Colorado, and Miami, Florida. It doesn't matter how I travel there. The altitude change between, let's say, the Washington Park right here and this little spot on the beach, it doesn't matter if I fly to Miami. It doesn't matter if I drive to Miami. It doesn't matter if I drive to Miami by driving up to Alaska first and then back down to Miami. It doesn't matter how I get between those 2 points. The altitude change between this little spot right here and this little spot right here where this person is laying is exactly the same, regardless of how you travel between those 2 points. So altitude change is another example of a state function, and Hess's Law says that energy changes in reactions are also state functions. They don't matter what the pathway is. So Hess's Law works, or it's a consequence of the law of conservation of energy. So here we have a reaction, and basically what Hess's Law is saying is, let's say A to B, that reaction, let's say that has a delta H of negative 100. What Hess's Law is saying is if we do this reaction by a different pathway, if we go A to C and then C to B, those two delta H's must sum to, also they must sum to negative 100 Celsius. So whether we go directly or whether we go in 2 steps, the energy change is negative 100 kilojoules. I think I said Celsius before, kilojoules. So this is what Hess's Law is saying. Now let's kind of examine why Hess's Law must be true by imagining we live in a world where it isn't true. What could we do if Hess's Law wasn't true? So don't write this down, okay? But let's just imagine we're living in a world where Hess's Law were not true, and what would happen, what would be the consequences of that. So this might blow some minds here, but let's do our best. So again, let's say that this going from A to B is negative 100 kilojoules of energy. So that would be exothermic. That would be something that we could get energy out of and we could use, like burning something. And so let's say in this alternate universe we live in that H1 is negative 40 and H2 is also negative 40. And that's impossible because negative 40 plus negative 40 is negative 80. So according to Hess's Law, that it cannot be true. But what if it was? Again, we're living in a world where Hess's Law isn't true. The other thing I would remind you of that we've talked about before is if you reverse a reaction, if you do a reaction backwards, it reverses the sign of delta H. So let's check this out. What if we're living in this world where Hess's Law isn't true and these numbers work? What could we do? Well, we could do this. I could turn A to B and I would get energy out of that. I would get 100 kilojoules worth of energy that I could use and I could do stuff with. Maybe generate electricity, run a car, or whatever. And then once I had B, I could turn B into C. So remember, this is supposed to be 40 here. But when we reverse it, it's positive 40. So I would spend 40 kilojoules of energy to get to C. And then I could turn C to A and spend another 40 kilojoules of energy. Well, that's only 80 kilojoules of energy that I've spent. And then but then I would have some A again. And I could turn A to B and get 100 kilojoules of energy. So I'm spending 80 kilojoules of energy, but getting 100. So each time I'm getting 20 kilojoules of free energy. So I could set up this cycle and generate energy infinitely forever for free. You know, set this up in your car and run your car forever without putting any fuel in your car, or generate electricity forever without any new fuel. That's impossible. It violates the law of conservation of energy, and that's why Hess's law is true. Now I know how some of you may feeling, looking right now. Maybe that wasn't quite clear, but just trust me, and you know, hopefully you got it. But Hess's law is a consequence of the law of conservation of energy. Don't worry so much if you don't understand all the finer details, but Hess's law is true. Trust me on that. So what we use Hess's law for is to calculate the delta H of a reaction that we don't know. Maybe there's a reaction we don't know. Maybe there's a reaction that's not even possible to perform, but we still would like to know the delta H of it for some reason. And we use other information that we do know to calculate that delta H. So we're going to see in this unit there's a bunch of ways to calculate delta H's of reactions that we don't know. And there's a few even just using Hess's law. We can do adding of reactions, we're going to talk about in a second. We can do heats of formation, bond enthalpies we'll talk about, not in this video, but at another time, and maybe even other ways. But there's a ton of ways to apply Hess's law, and as you'll see, this unit ends up being just a ton of different ways to calculate delta H. So let's look at adding of reactions first. It turns out that you can add chemical equations together in a way that's similar to adding mathematical equations. And you can take chemical equations and you can manipulate them. You can flip them, you can write them backwards, you can multiply them or divide them by any number. And as long as you do the same thing to whatever the delta H value is for that reaction, then you're fine. Then everything will work out. And as you'll see, what we're going to try to do is to add reactions into other reactions that we're interested in. When you're adding reactions, species or anything that is exactly the same on opposite sides of reaction arrows are going to cancel out. Whether they're in the same reaction or in different reactions, if they're on opposite sides of an arrow, they're going to cancel out. Species that are on the same size add together. They do need to be exactly the same, like water in the gas state would not cancel out with water in the liquid state, for instance. Or sodium with no charge would not cancel out with Na+. As long as they're exactly the same, they're going to cancel. So let me show you what I mean here. Here's what I would do. You should take the time to actually jot out these reactions, and you should write the little delta H's. So what I'm telling you is we can add these two reactions together, and we're going to get a third reaction. And the delta H for that third reaction is going to be these delta H's added together. So let me show you. Looking at our reactions here, we're looking for things that are exactly the same on both sides. Those things would cancel out. So for instance, the NO here is one thing. There's a 2NO on both sides. Those cancel. And then there's nothing else at all that cancels, so those cancel. These O2s, they're on the same side, so they're going to add together. So we have N2 plus 2O2 yields 2NO2. So now I've got a new reaction here that's different than either of these other ones. But I already know the delta H of this reaction because Hess's law tells us that the delta H of this reaction must be the same as those two added together. So the delta H for this third reaction here is positive 68 kilojoules, just this plus this. So that's kind of the general idea of how we can add reactions together and get delta H's for third reactions. Here's another example. What I would suggest is that I'm going to do a ton of practice with this in class. What I'd suggest is that for right now, you don't worry about like writing this down or anything, but instead just kind of kick back and watch me thinking here and watch me so you can see how I'm going to solve this. This is one of these things. It's often a little bit harder than it is. It looks harder than it is at first, I guess. But in Hess's law problems, often what we'll have is we'll have a series of reactions like these that we know the delta H for, and then we have another reaction, kind of our target reaction, that we don't know the delta H for. And our job is going to be to add these reactions, find a way to get these reactions to add to this reaction. But what we're almost always going to have to do is manipulate these reactions in some fashion. We can flip them, we can multiply them by any number, like I said, or divide them, as long as we do the same thing with the delta H. What I would advise is don't try to put the entire puzzle together in your mind at one time. Instead, look at little pieces of this reaction, look for things in this reaction, and see how we can change these to match. So, for instance, I've got a C4H8. It is on the right side of the reaction arrow. So if I'm going to add these reactions together, the only way a C4H8 is going to end up on the right side, obviously, is if it's on the right side up here. So I'm noticing I do have a reaction with C4H8 in it, but it's on the left side. But what I can do is I can flip that reaction in the middle. Watch. See, I just flipped it. I wrote it exactly backwards from the way, now it's back the way it was originally. Flip it, write it exactly backwards. The way it was originally, flipped exactly backwards. And I also flip the sign when I do that. I can flip the reaction as long as I flip the sign. And the advantage of that is now when I add these reactions together, the C4H8 is going to be on the correct side, which is the right side, when I'm bringing these down and adding them. Another thing I'm noticing is I need two H2s in here. And again, I'm not trying to put it all together at once. I'm just looking at little pieces. I see 2H2, I see 1H2. So what I could do is I could multiply everything in this reaction by 2. So multiply that by 2, multiply that by 2, multiply that by 2. You see what happens there? And then I also multiply this delta H by 2. And the advantage there is that's going to give me two H2s here. So when I add these reactions, that's going to look good. I'm noticing this right here, C4H4. That's also C4H4, so that kind of looks good. So let's just kind of see what happens. If we look for things that cancel, there is a 4CO2. See how there's a 4CO2 on both sides? Those cancel. And then we look for anything else that might cancel. And we have to look at all the reactions. Watch this. See how there's a 6H2 there, and there's a 6 O2s, 5 O2s, 1 O2. So I can cancel out those 6 O2s with that 5 and that 1. That's a total of 6 O2s there. So those all cancel. If there was one extra O2 or something over here on this side, it would just remain there. You just wouldn't cancel it out completely. But in this case, the oxygens cancel out completely. Here's another situation where 4 H2Os on this side cancel out with 2 H2Os on the other side. And that's everything that has canceled. So if we see what's left over, kind of circle that, you'll notice, and we drop down and we add them, we actually have this target reaction that I was looking for. And then, so therefore, I know the reaction of this by just adding these 3 delta H's. And I do that, and I get negative 158 kilojoules. So the delta H for this reaction is negative 158 kilojoules, or kilojoules per mole, which I've learned by adding all those up. Now, maybe that's a little mind-blowing. You know, I don't know. It depends. Again, we're gonna practice with this a little bit. Okay, in class we'll practice with a ton. You'll get used to it. It's really not as bad as it seems. But let's keep going, and we're gonna get the basic idea of all these methods, and then we're going to practice with them a bunch in class. There is another way you can use Hess's law, which is by using heats of formation. I'll remind you, heats of formation is the energy necessary to form something from its elements in their standard conditions. So that's the heat of formation. Heats of formation are things you can, for most compounds, you can look up their heat of formation in a book or in a table. Your data booklet has a heat of formation for lots of different things. Okay, probably the most important thing to note about this is the formula. The formula is the heat of a reaction that you don't know is going to be the sum of heat of formation of the products minus the sum of the heat of formation of the reactants. So we add up all the heat of formation of the products minus the heat of formation of the reactants. One thing you're going to keep in mind is since heat of formation is to form something from its elements, elements by definition have 0 heat of formation. So when you're looking on a table of heats of formation, oftentimes it either won't list elements sometimes, or if there's elements there, their heat of formation will be 0. So when we do these problems, just remember elements have zero heat of formation. So basically what we're imagining here from a Hess's law sense is we're taking our reactants and we're breaking them down into the elements. That's the opposite of heat of formation. So we're taking all of our reactants, breaking them down into the elements, and then from those elements, we're reforming them into the products. Now in the actual reaction, almost certainly that's not what's happening, but it doesn't matter if that's what's really happening because Hess's law says the pathway doesn't matter. So this is what I was just talking about. I don't think you necessarily need to write this down. I'm just trying to give you a little bit of a deeper understanding about what we mean when we use this and how Hess's law works. So if this is my reaction here, and I wouldn't know the delta H of it, what we're imagining is we are breaking CH4 down into its elements, which is carbon and hydrogen. Oxygen's already an element, so it doesn't have to be broken down. And then we are using these elements to form our products. So this is the heat of formation of our products, but it's actually the reverse of heat of formation of our reactants, which is why in the equation you subtract the heat of formation of the reactants because that reverses the sign. And again, I think that's mathematically for some people it's a little confusing, but that's the basis of why this works. These problems in particular, trust me, they're pretty easy. These heat formation problems, I know maybe the theory behind it sounds confusing, but to actually utilize this is something that we'll all be doing with relative ease pretty soon when we practice in class. But that's all for these notes, folks. Thank you very much, and have a good one. We'll see you next